the definite integral objectives. By this lesson, you should be able to evaluate definite integral using FTC Part 1, fundamental calculus. Understand the difference between a definite and indefinite integral, and then be able to apply this to a lot of problems. So what's the definite integral? If you remember when we first started talking about integration, it was the area of the curve. I was like, I'll give you like this, and I was like, blah, blah, blah. I was like, my integral goes from A to B, so you're like, okay, it's the area from A to the area to B. Well, that's what that definite integral is. But now how do we do it with algebra? Well, it's actually very simple. Here's the fundamental theorem of calculus. If you integrate with limits, that's what these are called. They're called limits. All it is once you integrate it, so once you get the original function back, you plug the top one in minus the bottom one. That's it. Top minus bottom. That's it. Integrate it, plug the top limit in minus the bottom limit. That's all it is. That's the fundamental theorem of calculus. Top minus bottom. Okay, so let's talk about some rules first. And we'll go back into that and do some examples afterwards. First, what we kind of mentioned before is the limits are the same. Well, remember, after you integrate, you're going to put the top minus the bottom. Well, they're both the same, you're going to get 0. So anytime the limits are the same, you get 0. This is kind of an important one. You're going to see that sometimes. So again, anytime it's the same limit, 0. Or underneath the curve, there's no curve, so 0. If you switch the limits, that's what this one does. You notice how it goes from B to A, then from A to B. Then it negates it. So let me go back up here, right? So I didn't do an example. I should do a quick example. Here's 3 to 3 of, I don't know, 2x plus 1. You don't need to do any work. You're like, oh, they're both the same? 0. This one says this. If you're integrating from 0 to 2 of x squared, and I tell you that equals 8, doesn't really matter. Then if you look and I go, oh, what's the integral from 2 to 0 of x squared? You'd say negative 8. Because all you did was switch the limits. That's the whole idea. So if you switch the limits, you negate it. When we've been using a bit, right? If you have a constant, you can pull it out. That's all that's saying, right? So if we're integrating 3x squared from 0 to 2, it's the same thing as saying, hey, pull the 3 out. 0 to 2 of x squared. Right, so you always pull out a constant. It makes life easier. Sometimes it doesn't matter, but sometimes it makes life easier. The next one, this one's important. It's like the transitive rule for integration. You go from A to B, and then you're going to go from B to C. So you notice how they match? Well, that equals this integral from A to C. So what's going on here? Let's say we gave you this thing. They said, what's there between A to B? Right, area between this curve. And then we're going to go from B to C. Well, doesn't it make sense if you add this one plus that one, you get the whole integral from A to C? That's all it's saying. Right, if you're going from A to B, and then from B to C, well, the area into this curve plus area into that curve isn't equal to the whole area. So that's all it is. So it's like transit property. If they connect, you just kind of add them up. So I said, let's integrate from 0 to 2 of f of x, plus integral from 2 to 7 of f of x. Well, they'll just equal, like, oh, they match, they connect. So 0 to 7. That's all that's saying. And then the last one, oh, here's a little proof of the one we did earlier, right? It's just better, picture's a little cleaner, but whatever, same idea, right? A to B plus B to C, the integral, that equals the whole integral from A to C. So they should right there. But back to this, right? The one we've been using a lot, you can separate it. If you're integrating two things, if you want, you can separate them. They keep the same limits, but that's how you integrate it. So if we're doing the integral of 0 to 3 of x squared plus e to the x dx, if you want, you can separate it out and go 0 to 3 of x squared plus 0 to 3 of e to the x. You get the exact same answer. Right? So a couple of new rules, a couple old ones, right? Classic. If they're just, the limits are the same, you automatically get 0. Here's a new one, right? If you switch the limits, it's an important one, then it negates it. That's all it is. So if you see the limit switch, you negate it. You can pull out the constant. That's an oldie, but an old classic. Here's another new one, right? It's like the transitive property. they connect, you just kind of add them both together. And then that's another old one. Okay, so let's do an actual example that we talked about earlier. Let's actually integrate with limits. So step 1, right? Integrate the thing. Right, this is a basic power rule. You add 1 to the power, divide by any power. So we're going to get x cubed over 3. Now this is our in-between step that common for mathematics. So you just want to integrate it. Then what you can do here is you put a little line and you put 1 to 3. That lets us know, and you let yourself know that, hey, I've integrated it. I haven't plugged in my limits yet though. So you integrate it, and then you put the little line to let you know, okay, next thing I do is put my limits in. Now remember that the fundamental theorem of calculus says it's top minus bottom. So we're going to plug in 3 minus plugging in 1 to the whole thing. And that's how we're going to do limits. Once you do this, you take the power, so 27 over 3 minus 1 over 3, and I get 26 over 3. That's it. That's how you do integration with limits. You integrate like you normally do. If there's limits, you put the top limit minus the bottom limit. That's it. Top minus bottom. So another one. Or 2 or 3. So this one right here. So we're integrating from 1 to 3 of x squared plus 2. So now notice that's the basic limit. Power for both of them. So we're going to add 1 to the power, divide by any power. That's a constant, just add the x. So my new limits, I integrated like this. And then again, we integrated and then we're going from 1 to 3. One thing I forgot to mention, we don't need a constant. We know we're integrating, so there's no constant in it, right? We're going from 1 to 3. You don't do the constant on when you have limits, because you know what you're dealing with. It's the same thing here. Oh, we're going from 1 to 3. You integrate it. You don't need to put a c because I have limits, so I get this. And once we get there, then it says top minus bottom, right? So you integrate it, have this in between step to let you know, okay, I've integrated it, but I haven't put the limits in yet. Now we can put the limits in. Also gives you points in case you plug the limits in wrong, but you did the integration correctly. Now remember, it's the top one minus all the bottom. So parentheses are important. Not being sloppy is important. Mathematically sloppy, I should say. Right? It's all the top minus all the bottom. So over here is like 27 over 3 plus 6. Over here is 1/3 plus 2. And then whatever that is minus whatever that is, because I don't want to do that, is your answer. Yay. Right, but it's the same concept. Integrate like normal, plug in your limits. Okay, the next one. Next one's a little special. If you notice this next one, it's not a basic one. There's a 2x there. So you could do reverse chain rule. You could do U sub if you want. But let's do a little reverse chain rule. So if we're doing reverse chain rule, we're going to take the integral of the outside, which is z. Leave the inside alone, 2x. And we're going to divide by derivative of the inside. Derivative of the inside is 2, so we're going to divide by 2, so 1 over 2. And then we're taking our limits from 0 to 2. Right, so you integrate like normal, and then plug your limits in. So in this case, we're going to plug top minus bottom. So e to the 2 times 2 times 1/2 minus e to the 2 times 0 times 1/2. Alright, so again, just integrate like you normally would. It's a little harder to integrate than normal. This was like a reverse chain rule. But once you do that, it's the same thing, top minus bottom. Over here, I get 1/2 e to the 4th minus 1/2 e to the 0. Now, keep in mind, this is not 0. E to the 0 is 1. So that 1/2 is still kicking. It's 1/2 e to the 4th minus 1/2. Again, no plus c because we have limits. You don't do plus c with limits. By the way, if you want to make that a little prettier, you can. That's fine. But again, if I make it a little prettier, if you're like OCD, that's also good. Let's move on. Some more. So look at this one. We're doing a sine one. Ooh. Right, so this right here, again, this integrate like normal. So the integral of sine, negative cosine. And I haven't plugged my limits yet, so we'll put 0 to pi over 3. Right, this little in-between step so you show that, hey, I know how to integrate, and I know I gotta do my limits still. Now we put the top minus bottom, so negative cosine pi over 3 minus negative cosine 0. Cosine pi over 3, it's 60 degrees, so like this. Rad 3, because 60 is big. 1, 2. Cosine's so 1/2. So negative 1/2. Minus negative cosine 0. Cosine 0 is right here. 1, 0. So this is negative 1. Double negatives make a positive. Negative 1/2 plus 1 is just 1/2. Right, so I went faster to do the trig than I normally do, but it's trig. You gotta get there. That's not a straight line. But whatever, one take, let's go. So this one, right, same idea. Now look at this one, it's a little more messy. I'm gonna separate it, because that's to make it a little easier. We're gonna use one of the rules. So 2x from 1 to 4 dx. And I didn't want to deal with all this at once. I'm gonna separate it and do. No, actually, I'm gonna plot the 3 also, because I'm like having a 3 there. 1 to 4 of x dx. Oh, 1 over x, sorry. So 3 on top. Right, so I'm gonna separate this. I think it makes life a little easier. So if I separate it, so keep the limits on both of them. Then what we're gonna do right here is integrate it. Add 1 to the power, divide by a new power. We get x squared from 1 to 4 plus 3. We're going to integral of 1 over x, natural log. So natural log of x from 1 to 4. This one, top minus bottom, so 4 squared minus 1 squared. Same idea here, top minus bottom, 3 natural log of 4 minus 3 natural log of 1. So this is going to be 16 minus 1 plus 3 natural log of 4. Anybody remember what natural log of 1 is? 0 is the right answer. So all I get is 15 plus 3 natural log of 4. Okay, so that's basic limits, right? It's a little review, but we did a lot of that was just like reviewing integration, but the general idea is the way you do limits, we would call it a definite integral. When you know how the limits, you call it indefinite integral. The way you do definite integrals is you integrate like normally do, and then you have your limits, plug the top one in minus the bottom one in. Now, what if we have to do u sub? Well, there's kind of 2 ways. One way is just do like you normally do. Integrate it, do your u sub, integrate it, plug it back in. At the very end, plug in your u, then plug in your limits. So you can do it that way like normal. Basically, don't change a thing. Integrate like you normally do. At the very end, after you plug in your u, plug in the limits. So that's one way. So way 1, treat it like normal. So let's do that. We'll do that in green. So let's just u sub this real quick. That's my u equals x cubed plus 1. Take a derivative. Right, the derivative of that's d over dx. Derivative of that is 3x squared. 1 goes away. So do some math. I'm going to do it really fast here. So times by dx divided by that. So du over 3x squared equals dx. Right, so I have everything I need. I have my dx, I have my u, plug it all in. So we're going to integrate from 0 to 2 x squared u to the 1/2 over du over du over 3x squared. X squareds cancel out. I'll pull out the 1/3 just for the sake of it. Now I can integrate this like normal. So add 1 raised to the power row, add 1 to your power, divide by new power, which in this case is 3/2. Remember the trick, bring the 2 to the front. So we're going to get this mess. 1/3, 2 over 3, u to the 3/2. And then don't forget you plug your u back in. So we're going to get this 2x cubed plus 1 to the 3/2 over 9. And I still got to plug in 0 and 2. Right, so that is just plug in 2 to everything and plug in 0 to everything. So 2 cubed plus 1 to the 3/2 over 9. minus 2, 0 cubed plus 1 to the 3 halves over 9. Again, this would be math. That's 8 plus 1. It's actually 9, 9, 3. I can actually do all this, but it's just math. Solve it. That's way 1. Right? Way 1's treat like you normally do. Just take the u sub, get your integral, which we did right here. Once you get your integral, plug in your limits, top minus bottom. That's the normal way. That's a cool way of doing it. Way 2 is you change your limits using the u. So this is what it will mean, right? Way 2 is right here. We still have u equals x cubed plus 1. So what's going to change is this. It's like, oh, we have 2 there, so let's plug that in. So I get a 9, and we have a 0 there. Plug that in. So I get a 1. These are the new limits. So if I look back and I plug everything in what we had, let's just start from like here, right? If I have 1/3 u to the 1/2 du, I can, instead of having to worry about plugging my u back in, I can just use my new limit, 1 and 9. So if I integrate this, I'm gonna get 1/3 u 2/3 to 2 3/2. I think that was the integral right there. Right, instead of having to plugging this stuff back in, I used to my limits here, 1 and 9. So it saves a little step, right? It saves a little bit. So instead of having to deal with plugging in 2 to x cubed plus 1, plugging in 0 to x cubed plus 1, we already did that. So I just plug in 1 and 9. So it's going to be like 2 and 9 to the 3/2 over 9 minus 2, 1 to the 3/2 over 9. Right, so it's a little better. It's kind of, honestly, it's kind of the same. But the thing I do care about is that something that IB might ask you is how to change your limits. And that's how you change your limits. Change your limits is easy. If you want to change your limits, just get your u value and plug the limits in. So the new bottom limit was plug the 0 in, so it'll be 1. The new top limit, plug the 2 in, it'll be 9. That's what I want to care more about. So I don't care which way you do it, but if they ever ask you to change the limits, you should know how to change the limits. Just plug it into the u. Easiest way to change limits. Plug into, that says plug u. So this is another one to practice. And honestly, we'll do this one quicker. So let's do our u real quick. U is x squared plus 1. Remember, it's not always the inside. If you're not sure, try to think it's a higher power. If they're both the same power, generally the bottom is what's going to do if it's a fraction. So this is my u. Let's look at our limits first. Let's worry about the limits. Right, so if I want to find new limits, we'll just plug these in. So let's plug in 1. So u is going to equal 1 squared plus 1, which is 2. And then 3 is going to equal squared plus 1, so that's going to be 10. So those are my new limits. So let's just do this real quick. So if that's my u, we got to take the derivative. So du over dx equals 2x. I'm just going to roll fast. Du over 2x equals dx. Just multiply and divide by 2x. Right, so now I can plug it all into my equation. So my new limits are 2 and 10. I have x over u, because that's a u, times du over 2x. That's a little messy, but remember what happened was I changed my limits, so 1, 3 became 2, 10. It was x over u, and then that dx turned into du over 2x. The x's cancel. As always, you can pull out the fraction if you want. So 1/2 integral of 2 to 10 of 1 over u du. Remember, the benefit of changing your limits is that I don't have to worry about plugging my u back in. I just integrate this and plug it in. So you integrate this natural log from 2 to 10, and then there you go, plug that in. 1/2 natural log of 10 minus natural log of 2. By the way, that's not natural log of 8. That's natural log of you divide natural log of 5. If you're really pro, you could get natural log of 5 to the 1/2. If you're really, really pro, natural log of square root of 5. But again, IB general takes that's fine, this is fine. Natural log of 8's wrong, but these would be fine, any of those. Okay, so about how you doing your calculator, you just plug it in. So if we go to math, now this only works for definite integrals. So notice you have to have limits. Right, you have to have limits for it to work. If you're trying to do it indefinite, right, if they don't have any limits, you can't do it. It only works with limits. So if you go to math, and then you go down to FN, on your calculator, if you have a TI 84 or 85 or whatever, if you have Casio, get out of here. And then it would literally just show you like this. It'll be like that. You could type in your equation, you can put the limits in, comma, dx, and you can put the value in there, and they'll get you your answer. I would show you, but my trial period ran out, so sorry. But if you want to try it, when I did it on my calculator, I got 586.2635805. So I got around there. So you could check and go over in class. Okay, last kind of big idea for what we're doing today. How do you do different integrals? So remember all the properties we talked about? Right, so if you switch the limits, then it's negated. You could pull out a constant. There's a transitive property one where if you go to A to B, then B to C, right? You're just talking about areas. So area of this thing plus area of that thing is the area of the whole thing. So A to C. And you can separate them. Well, we're going to use these properties to do things of just generic integrals. So let me show what I mean by that. So this is the first one. If the integral from 1 to 3 is 2, they tell you the integral from 1 to 6 is -3. Find 3 to 6. So they gave me 1 to 3, 1 to 6, and now I got to find 3 to 6. So it's kind of like a jigsaw puzzle. How do these connect? Well, if I go 1 to 3 plus 3 to 6, isn't that going to equal 1 to 6? So right, if we do integral from 1 to 3 plus integral from 3 to 6, it should equal the integral from 1 to 6 because these connect are just different areas. Okay, so, well, they told me what this one is. This is 2. This is what we're looking for, so we'll make it x. And they told me that one's -3. So, do a little algebra. X equals -5. So the integral from 3 to 6 is -5. It must be below the x-axis. But stuff like that, right? You got to use the properties we know. We know if we connect 1 to 3 to 3 to 6, it equals the whole thing. Plug it in and solve. This is the next one. This next one's a little more about what Ivy likes to do. So here's the key. If the integral from 1 to 4 of f of x equals 3, find all these. Look at this first one. Integral 1 to 4 equals 2f of x. Well, that 2's not there. That 2's not in the original. So let's pull it out because we could do that. So it's 2 integral 1 to 4 of f of x dx. Well, this I know. They told me. Right? When you see this, it's 3. So this is just 2 times 3. So 6. That's all that one is. You pull the 2 out. Oh, it's the thing they gave me. That's 3. So 2 times 3 is 6. Look at this next one. Right, remember again, they gave me 1 to 4. This is 1 to 2 and 4 to 2. What's going on there? Well, I got to try to make this 1 to 4. So let's flip this. Notice the limits are off. So let's flip that around. So 1 to 2. If you flip the limits, doesn't that negate it? There's already negative there, so it's become plus 2 to 4. Now remember, these match. 1 to 2, 2 to 4, that just gets you the whole 1 to 4. And we know what that is. They gave it to us. It's 3. So the answer to all this is just 3. Once you flip it, you get positive 2 to 4. Well, now you can connect them because these two matching, you're just adding areas. This area plus that area equals the whole area. And 1 to 4 is just 3. Now the next two are a little tougher. So look at this one. I have this plus 1 there that's in my way. How about we separate it? Because that's a rule we could do. 1 to 4 of f of x plus integral 1 to 4 of 1. Now this I know, they told me that equals 3. So all this, just 3. This side, they don't tell me anything. What you do here is you actually just integrate it. Actually do the work. So the integral of 1 is 1x. We have limits. Right, so limit from 1 to 4. So remember the way we do this? Top minus bottom. So 4 minus 1, which is 3. Add it to the 3 we already had, and we get 6. So let's try that exact same property, that exact same data right here with this one. Right, same concept. They give you 1 to 4 f of x plus 2x. So again, we're going to separate it. Integral of 1 to 4 of f of x plus integral of 1 to 4 of 2x. This they gave me. That's 3. Don't have to worry about that one. This one, I actually got to do it. It can't be lazy. Add 1 to the power, divide by a new power. Lucky for us, the 2's cancel. I get x squared. I have limits. I'm going from 1 to 4. The way we do limits, top minus bottom. So 4 squared minus 1 squared. So 16 minus 1, or also known as 15. Add that to the 3, and you get a total score of 18. All right, so all we're doing is using the properties. You can separate them. Using the properties, you can integrate them. All that stuff. Let's do one final one to make sure we have this. So let's look at this one. Let f prime of x equals f of x, and integral from 2 to 7 of f of x dx equals 9. If capital F of 7 equals 4, find capital F of 2. Okay, so what's going on here is this. Let's integrate this. Remember when you integrate f of x, how we write it? Write it with the capital. So the integral of that's going to be capital F of x. Right? But remember, we have limits, so that means we're going to go from 2 to 9. 2 to 7, sorry. So that 9 got in my way. And then when I integrate this, it tells me it should equal 9. Don't ask me why it's all slanted. Right, so again, let's go over that again. Right, when you integrate a function, remember it goes 1 up. It goes to capital. It's like if this was velocity, you would have acceleration. You would have the original function, sorry. You go 1 up 1, right? So if you integrate lowercase f, you get capital F. Since there's limits, you go from, you write down your limits. So we integrate it, so now our limits are 7 to 2, 2 to 7. And they tell us it equals 9. What's the next step? Well, what's the fundamental calculus? Top minus bottom. F of 7 minus f of 2 equals 9. Well, that's 9. F of 7 tell me is 4. And I'm looking for this thing. So, do a little math. Add f of, subtract 4 from both sides. Negative f of 2 equals 5. Divide by negative 1. F of 2 equals negative 5. And that's the idea. That's definite integrals, right? It's all about integrate like you normally would. So you integrate, and then once you get your limits, if you have limits, top minus bottom. That's a definite integral. So this is indefinite. Notice how there's no limits. What's the difference here? Once you integrate it, you have to put plus c, right? Because there's no limits. This is a definite integral. This one you can put in your calculator if you let's use a calculator. Right? The difference with this one is once you integrate it, it's top minus bottom. So f of 2 minus f of 0. Right? So definite integrals, top minus, once you integrate it, top minus bottom. Indefinite, plus c. And there we go.